No solar cell. There is nothing called like anything. Nobody, no cell, nothing is there. Only a silicon or germanium diode will be there. Okay, there's an incident sunlight. No. So there's a light is in, so it will go and break the covalent bond, and we have here depletion layer, electrostatic field, and there's a p-type and type that I indicated. So now a covalent bond will break up. This incident light, it will have some wavelength. It will break up the covalent bond. Any covalent bond breaks up due to incident light. So this all should move like this, no? And the electron should move like this. That's what O will shift the depletion layer only. Now the all electron pairs that are generated due to incident light, and what is the basic necessity? Sc, the lambda should be less than or equal to Sc. You can't put no condition for lambda. What you should put? You should put condition for the band gap. For solar cell, what is the condition? The energy should be, the band gap energy should be greater than. For the photoelectrons, for the incident light to generate photoelectrons, shall we put like this? Okay, so sorry, it should be. There's a condition for this one. So what should be the band gap? So don't put condition for lambda. Can you ask sunlight to change lambda, to change intensity? All these are fixed, no? Intensity and lambda, nothing to do with this. No more changes here. Now what all changes you should make for this one? So I have come like this. I'm not going to disturb lambda here. So the band gap of the material should be so adjusted that it should accommodate this particular thing. So the incident photon should able to liberate the photo like a minority carriers, should able to break up the covalent bond. So like that the material should be again same thing, silicon germanium will pick up here. Because this lambda is a strict condition for us. Oh no, these electron hole pair generated. This holes will go and occupy here, and these electrons will occupy. What we'll get after this? What we'll get? So shall I say shall be some sort of deposition of electrons here, and there'll be deposition of what, like an holes here. So this will become positive charged layer. This will become negative charge. But already this is there. We are not talking. You can say like a what is the like a intensity of light? Millions of photons will come. Millions of minority carriers generated. So we'll get an accumulation of holes here. We'll get accumulation of electrons. And how do that field will be generated? I'll make it a little bit small, all these things. The next thing. So what is the band gap of the material? EG should be, okay, now shall we put like accumulation, so this end will become positive, this will become negative. So shall I say some potential difference is generated, that is what VOC. How do that accumulation of holes will occur here? Here what happen? Accumulation of, so when light is incident and if the energy of photon is sufficient to break up the covalent bond, we'll get minority carriers generated. These minority carriers, what happen, will be drifted by the electrostatic field present in depletion layer. The holes will be drifted towards p type, electrons will be drifted towards n type. So I'll get here continuous, like this continuously the light will be incident and there'll be drifting of charges, so accumulation of holes. And now you can ask questions, sir, like this, one day there won't be covalent bond to break up, and making and breaking up of covalent bond will occur, and there'll be some constant, means one, what you have to ask question for teacher is, sir, one fine day there won't be any fully covalent bond, we don't get a covalent bond of this kind, because the sunlight will be continuously incident. One day what will happen? There won't be covalent bond. Is it like that? You know enough some chemistry. Can it happen really? And there's an electrostatic field of depletion there. So here you see that one. So as the electron it acquires, no, so there'll be some field, no, here. So how long this will occur is, so now this positive charge, no, so this will produce an electrostatic field, and at one instant open it will stop. So what will stop is, like, the drifting will stop here. The reason for that, the electrostatic field produced by these particular layers, I'll call this like a some plate, that's like a terminal, so what you can call. So the field will be produced here. When that field produced by the accumulation of the charges, electron and holes at the ends, if it is balanced by the field produced by depletion layer, tell me, like, what is the net field here? Will be zero. So though a covalent bond will break up, the minority carriers here will not get drifted. And though the moment they're generated, again they'll come back here. So this what happens here. So what we are discussing is this initially. After some time, the field produced by this accumulation of charges will be towards right. When these two fields will balance, no more further drift. And the potential difference across this will remain constant. So how long it will happen? Within, I think, some 5-10 minutes. Within 5 minutes, what happen? We'll get there will get a constant potential difference. That is called like a open circuited voltage. Open circuited voltage, this one. And no more further drifting will occur. No more further accumulation of charges will occur. Why that will happen is because of the field produced by this. I think books have not shown. So for your convenient, I'll just show it so that it'll be easy for you to understand the concept. So from where this field I'm bringing, this, shall we write some symbols? E1, this is E2. Uh, in the absence of light, this is what happens here. E1 will be there. Now, what is E2? E1, we'll write it here. E1 is field due to depletion layer. What about E2? Field due to accumulated charges in P and N type material. Okay, once when E1 becomes equal to E2, no more further accumulation of charge and a constant potential difference is brought here. Okay, this there, I think I'll better remove this because again we have to go to a lot of explanation. Nobody will ask you any question, so I'll take it out. because even at our level, no discussion is there. But practically, this is what happens. I'll remove this. So we'll not go for other than out of syllabus things. Okay, let's assume that one. So this is what happens. Okay, let's think. This is the open circuited voltage. Then what we get is, sir, is it possible for E2 to become greater than E1 when you connect a load? We'll never use this VOC. Yeah? Just I'm giving explanation here. We'll never use this VOC. Means it's of no use. Huh? I'll just keep the solar cell in sunlight. What is use of this? No use. We should use for some application. That's why the books avoid it. Okay, now I will short circuit it. I will short circuit it. What do you mean by short circuit? We are going to connect a wire like this, where the electron will flow, because I should not show the moment of fall. I should not show the moment of fall. So therefore, this electron will flow like this. Opposite to flow of electron is short circuit current. Agree this? This will be now how that flow of charges, everything. Incident light. This will have lambda and intensity. So this light will be incident. All electron pair generated. So this electron will come here. At this end is positive. This is negative. So this electron, so what happen, will start moving like this here. Because here number of electrons are less, so there is a path. So this electron will go like this here. It will come. So the moment electron comes here, so how the electrostatic field in this region will be towards left, no? So this electron will experience a force. So like that what happen, the overall material, the breaking and covalent bond will continuously will take place. If you're interested, you further analyze. I'll just showing that it will take place here. Because we will again here what happen, the making up of covalent bond, how do it will occur? So you can put like this. The moment this electron will come, because of this field, because of this field, so sorry, this is positive. Now this potential difference setup what happen in what direction will produce field in this direction, and the electron comes here. So like that, the breaking and making of covalent bond will occur. I think that you don't bother, and this also like a we don't use much in application. This is so this is short circuit current. This one. Next what happen? Usually we'll connect a load, we'll connect one resistor, and the heat generated across resistor is what use it for application. So when I plot the graph, I think the last 5 minutes I'll wind up this topic. So how the curve? This will be the curve. Huh? Not semicircle. It is not semicircle. This is open circuited voltage. This is short circuited current. So if you operate like this, we'll get just potential difference. We don't have current. If you operate here in this region, you'll get a current, but no potential difference. But what we need power, no? So to get a power output, I should operate here. So usually what happen, we prefer more current, no, than the voltage. So therefore, what is the operating point for this? The operating point will come here. This is the operating region. For that, what shall I do? I'm going to take this solar cell. So how to operate there? I'm going to connect one resistor here. This is called like a load RL, and any heat generated across it will be the what you I'll let this be heater coil. I'll immerse this in water, and sunlight, what happen, what the solar will do, will convert sunlight into electrical energy, and this resistor what do, will convert heat energy into, will convert electrical energy into heat energy, and the water will get boiled here. This is a load. This is very important. So when I operate here, I'll see that the diode, the solar cell will be operated in this region. So we'll get maximum current because I square R is what very important, no, than V square R. So this will be operating point here. So I think now if I just use only in this mode, what is use of this? I'm unable to take out power from the solar cell, no? And what about this? I'm unable to take out the power from solar cell. It's of no use. So therefore, so we'll always do like this here. So I should take out the power from the solar cell because continuously light is incident, continuously energy is incident, continuously the energy from solar cell should be taken. So we go for operating region here, not this one. So in the exams, how do they test? They test with simple questions like this here. They test with simple questions like what should be the operating point for the solar cell? Either 1, 2, or 3. It should be 2. If you operate here, you'll get more voltage, less current, but I square R is what needed for application. So therefore, this is the operating point. You can take this also. But V square R, I square R is what power is needed, no? We have to extract power. So this is the operating point here. And now if there are two solar cells are there, if there are two solar cells are there, and the graph for them will be like this. Which particular solar cell we should prefer? This is solar cell X, Y. The area in their VI graph, the area under the curve will generate more power, no? The area under this VI graph will be what? Like a power generated by solar cell. Area under the curve, VI graph, is proportional to power generated by solar cell. So this having area. So therefore Py greater than Px. So which solar cell will generate more power? So like that, for different materials, I'll plot the curve, the area of that curve. What will indicate here? So those materials which are having more area, that particular solar cells will be inside. For the same incident light, I'm not telling the incident light, sunlight, we can't do anything. There's a basic idea of the solar cell here. So they can ask you graph, operating region, and some small ideas, anything here. Okay, I think thank you for your patience. It was a marathon class. It seems almost like 3 hours, 3 hours 15. Okay, any doubts you can clarify later on. I'll wind up.